Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about projectile motion and parabolas. So, quick little inspiration here, right? In kinematics, you're talking typically about physics and the study of motion. So a lot of people hear these kinematics equations, right? So we're getting up towards the AP Physics exams. So the kinematics equations definitely show up on those exams. We have equations like Vx equals Vx initial. So that's what the 0 means here, plus the acceleration in the x direction times time. Then you also have your position. X is x initial plus Vx initial times time plus 1/2 at squared. We have this third one here. Velocity squared is velocity initial squared plus 2 times the acceleration times the change in position. There's all kinds of different equations here. Now, as far as the math is concerned and things like that, the first two equations definitely can be used to find the third. Really, the second equation is the most important if you know some calculus and you know the physics involved with the calculus stuff there too. You can definitely derive all of these things very simply in this case. Now, a little bit of a preview of something we're going to talk about later is that I do want to stress here that everything in this screen, these kinematics equations, are one-dimensional kinematics equations, right? So this x here doesn't necessarily need to be horizontal motion. It could be vertical motion. We'll see some swaps there in a second, but these equations definitely involve only one-dimensional motion as well. So let's take a look at these here and ask the question, right? So we have this position graph. This is our main graph that we're thinking about and we want to look at there. So x is the initial x position plus the velocity times time plus 1/2 at squared. Now this graph is a parabola, right? So if we look at this, we have the t squared, t constant term. Those are our ABC if you're used to kind of ax squared or at squared plus by plus c in this case. Now, as I mentioned before, right, this is a function of position versus time. So that might be a little bit different than we're thinking about there. So we're going to look at an example graph of this in a second, but I just want to point this out now, and I'll say a little bit more when we kind of talk about that graph in this case. Now, one other thing I want to mention here is that for our purposes today, and most of the purposes for physics, the typical example is that A is going to be equal to gravity. So we're typically doing, okay, a ball is thrown or a ball is dropped or things like that. And then the acceleration is due to gravity. It's falling that way. So this is negative 9.8. We're not going to be too worried about the units or things like that. But the approximation we're going to use is negative 9.8 meters per second squared for this acceleration here. So let's see that in action with the simple example. So graph the motion of a ball thrown upwards with an initial speed of 5 meters per second from an initial height of 1 meter. So writing out all of our important information given in the problem. So given in the problem, our initial height. So the initial height is 1 meter. Now this is vertical. So just setting the table a little bit, let me talk of this here, not in terms of x, but y initial. So the y initial is 1 meter. We have the initial velocity in the y direction given to us as 5 meters per second. And so we don't need to worry about the units there as well. And let's just write this a down right away too. So a is negative 9.8. So we're given all of those those pieces of information really in the problem there. So that kind of is all given to us, even if the acceleration isn't mentioned there, it's acceleration due to gravity. Now, I'm going to stress here that we're coming up with an equation for y in terms of t. So this equation, you can look back, is the initial position. So we have 1, and then we have plus 5 times t. So that is the initial velocity times t. And then we have minus 1/2 acceleration. So this one comes up so many times. Once you do a couple of these physics problems, you'll be so used to seeing negative 4.9, which is 9.8 divided by 2. And then we have a t squared in this case. So this is a quadratic graph. And let's take a look at this here. The last thing I do want to stress quickly is that, remember, this is in terms of y versus t. So our y-axis is y, the height, if you like, and then we're graphing this versus time. If you actually just looked at this ball, of course, it would go up and then fall straight back down, right? The motion would be just up and down if we were looking at it there. But our graph in terms of the y-t plane is a parabola that we have in this case. Okay, now let's take a look at a two-dimensional example next. Now, this one is a little bit different and seems a little bit messy, but it's actually not going to be too bad in this scenario. So let me start out by writing out the two equations we have. So we can have x of t, so the x motion. This is why it's starting to get good at thinking about x's and y's. So we have the initial x position plus the velocity initial in the x direction times t plus 1/2 a in the x direction t squared. Now, right off the bat, let's make a couple of comments in this scenario. So first of all, is there an initial position in the x direction, right? Well, if we're throwing this ball or something, we're saying it's thrown from an initial height, so a person might be standing or things like that there. But we could say the x position is nothing. So let's just get rid of that right away. Now, for our purposes here, slight spoilers for the questions that I want you to think about for next week. But in this case, we're saying gravity is pulling the ball down. Is that doing anything about its horizontal speed, its horizontal velocity? No. So we actually just have this motion in the x direction is the velocity initial in the x direction times time. Now, how could we go about figuring out what that is going to be? Well, if we look at this here, right, we do have that our initial speed is 5√2 meters per second. Now, if you've seen this before, this will seem totally natural. If you haven't seen this before, this is a little bit weird. But even though this is a speed, we know that it's this 45-degree angle. The speeds actually work just like distances in a sense. We can break down this speed just like you would draw a right triangle here. This is a 45, 45, 90 triangle. You can actually break the speed down in the same exact way. So when we say that there's initial speed of 5√2 at an angle of 45 degrees, what we can really do and how we work with this is actually we can break this down into 5 meters per second in both directions. So we have 5 times t in the x direction, and we're going to have a 5 times t in the y direction as well. So without further ado, let's write out that y direction as well. So let's do this one a little bit quicker there. So it's y initial, so the initial height, the initial y value is 1. we just said its speed in the y direction is also 5 meters per second initially, but this one is accelerating downwards, right? Gravity is pulling this down there. So we actually end up with the same equation that we had before. So we have the y position is 1 plus 5t minus 4.9t squared. The x position as a function of time is 5t. Now, this is what's called a parametric function. So this is parametric in this case, and I'll have you think about that a little bit more on the homework, right? You could think about substituting x into y or stuff like that, but you can actually just graph these directly. So without spending too much time here, I do want to show our graph in this case that again looks like a parabola, and in fact is a parabola here too. So we have this graph now in this scenario, and to stress again, this is actually graphing the y position versus the x position. So in the previous example, we were saying that ball was going up and down. The parabola, in a sense, came from the position versus time. But here, actually, our ball is flowing through the air. If you took a picture or a video of it from the side, you would see this parabolic graph. You would see this parabolic motion in this case there. Now, let's see how this stuff works in general a bit as your question for the week. So, in general, this two-dimensional projectile motion acceleration is due to gravity. We can write out two equations, one for the x. This should look fairly familiar. X initial position plus initial velocity in the x direction times time. Y initial y position, velocity in the y direction times time minus our 4.9t squared. So this isn't too difficult, but explain why this results in a parabola if you turn this all into xy graphs or graph this parabolically. Explain why you're going to end up getting a parabola at the end. And also, think about why this is actually useful. This is stressed a lot, not only because it's a fairly nice result, but there are some nice properties that we typically know of for parabolas that can be helpful when we're interpreting this motion graph. And that's one of the reasons this idea is used a lot when teaching physics there. Now, let's complicate things a little bit with our second question here. So if we think about real life examples, so you throw a baseball, you hit a baseball and it's going for a home run and you want to look at its path. You think about golf, somebody driving off the tee or an approach shot onto the green or things like that. So these 2D motions kind of there. In fact, they do not follow perfect parabolas there. Now, before we say all of this stuff is a lie or things like that, perfect is a pretty important word here. For a lot of scenarios, for a lot of approximations, if you think about it as a parabola, you're going to get pretty much the correct answer. It's going to be pretty close to what happens in real life, but not quite. Actually, there are some differences in this case, and I challenge you to think about that a little bit, maybe try to do some research about that. Why do they not follow perfect parabolas? What assumptions are we making in our equations today that don't actually follow the real world applications? But with that, that will be good for today's video. So stay tuned for the continuation. Think about those questions during the week. If you have further follow-ups or questions, let us know in the comments. And as always, if you liked this video, please give it a like, subscribe so you can keep watching, share ideas for upcoming videos with us as well. Otherwise, I will see everyone next time. Goodbye.